Hi, welcome to Ethereal Mechanics Behind the Scenes number 6. We discuss Ethereal Mechanics, recent developments, and the path forward. And I'd like to apologize for the long delay between the videos. But things have been going good, so it's actually for a good reason. Oops, too far ahead. So we've had success on all fronts. Ethereal Mechanics proper, plus the Q algebra, foundation series, new wave theory, rules of acquisition. Obviously, these are all supporting functions of Ethereal Mechanics. And we're going to start with the foundation series. As you recall, we stopped in the foundation series because by me revisiting what I did 20 years ago, I found that I made a mistake. I had thought I had rationalized this model over this model. In fact, there must have been a mistake because no matter what I did for closed-loop experiments, neither of these models gave me any better results than the other. Clear case of what we're going to show you of rule of acquisition number 11, which is coming up, that there can be more than one model existing that gives experimentally identical results. And so this idea of monotheorism, where there's only one theory, is false. And anybody who thinks that way is really short-sighted. But let's get on with how we're going to resolve this. We are going to reduce this. Okay. Let me back up. If you recall the video, we actually had four sets of data that all gave us the same answer. Jackson, but if we subtract, Jackson was wrong derivation only because Jackson included intrinsic inductance or internal inductance, depending how you've been taught it was. So Jackson's actually okay if you just remove the internal inductance, and that's what this is. And you can see these four different models all give the same, pretty much the same answer within experimental accuracy. And as you recall, Maxwell's mutual inducting is just simply if you have a loop of wire and taking this cross section, if you put all the current at the center of the wire and you put a test loop at the edge of the wire, and you compute the mutual inductance between the filament area at the center of the wire to the current through the loop of wire at the edge of the wire, you get a fantastically good result for self-inductance. It's really remarkable. And it's completely wrong. It's completely bogus. And this shows you how completely wrong models can give you the right answer. So just because you get correct answers does not mean you have the right model or theory. This is the rules of acquisition coming back to us in droves. And the models I found through searching were 5008 and 5079, and they give experiment. And that's what these two guys are. These are shown in field format. So the recent development I have is a method of disambiguating. That's what we have to do when we have more than one theory. You have to disambiguate. And also rule of acquisition 17. If you've got identical answers, there might actually be a lower model that explains both of these, a much more fundamental explanation. So we have to be open to the rules of acquisition that say there might be a more fundamental model than this. So what I'm going to do first is a dipole simulation, because all these were closed loop experiments, and that constraint of the closed loop is what caused the ambiguity. And therefore the solution is twofold. We can either go open loop or high voltage. The easiest way to go first is open loop. And since the classical definitions, Jackson and the Maxwell mutual use vector magnetic potentials, and according to the classical textbooks, vector magnetic potentials mean absolutely nothing if the loops considered are not closed. And since we're opening the loop, that means vector magnetic potentials mean absolutely diddly squat. Therefore, these models do not apply here. That leaves either of these two models here. Okay, so therefore, if I take a simulated source loop and I rotate them around 360 degrees around take a target loop and rotate it around 360 to this loop with different current densities in the loop, that's going to matter, then I should be able to get the proper field of a dipole antenna. Okay, if it's this one, I'm only going to get basically a field pattern that pretty much looks like that. If it's this one, I'm going to get a field pattern that's pretty much spherical. And that will be a way to disambiguate the two. It should be. If it doesn't, we got more work to do. But that's okay. don't want science to be done too quickly because I don't want to get bored in life if science is all done. Q algebra, using the rule of acquisition 17, prior knowledge is problematic, had a breakthrough on multiple barriers because of prior knowledge. We're going to have more details about that later. The reason why I'm holding Q algebra close to my vest is because Q algebra is the way I'm protecting ethereal mechanics from plagiarism. New wave theory. Fixed a problem with the misshapen waves. If you'd seen the simulations, which are still there, you'll notice that the wave fronts kind of had a diagonal or diamond shape as opposed to a circular shape. That was caused by a numerical integration error. And I also have refactored the code to use CUDA. CUDA is a parallel processing paradigm that uses your graphic card parallel processors to speed things up. And I've got over 100 times performance improvement. And because of that, I've extended the CUDA simulations to do 3D simulations, because obviously in the past we were just trying to get the whole thing to work with just 2D. But we have to do 3D to get the full effects that we're looking for, because an irrotational flow is not likely to happen on a 2D simulation. I think an irrotational flow needs a 3D simulation. And the other thing that was done with the new 3D simulation is to assume viscosity in the medium. And what that has shown in the simulation is that higher frequencies are attenuated faster over distance than lower frequencies. This is causing waves to redden, not redshift, to redden. Just like the setting sun is not redshifted, it's reddened. Okay, so what I want you to do, and we're going to cover, this homework is going to be covered in the next release of the new wave theory, which was supposed to be during this set of releases, but I got tied up for reasons I'll explain. So what I want you to do for homework is look up the two ways scientists measure redshift of distant galaxies. There's one method called spectral redshift. There's another one called photometric redshift. Which one is used 99% of the time when measuring the redshift of distant galaxies? And how will reddening of light affect our present view of the universe? In other words, if the light coming from those distant galaxies are reddened and not redshifted, what does that really mean? And we're going to go over this in the next video. I need to put more research into this before I tell you my conclusion, just to make sure I dotted my I's and crossed my T's. Oh, and the homework from last time, if you watched that quantum mechanics show, it's amazing that in the beginning they have like 10 or 15 scientists go and say, oh yeah, quantum mechanics has not failed to provide one correct answer. And at the end of the show they're saying quantum mechanics doesn't predict anything in the real world. So wait a minute, okay, so what they said in the beginning was a bunch of lies, because if your theory doesn't predict something, your theory is wrong. And you can't use the argument, well, it's just for small scale, because the whole point of this is to find a unified field theory that predicts everything. So you can't have a unified field theory that only applies to small. If you're going to have a unified field theory, it's got to apply to everything at all scales. And I think ethereal mechanics is going to be the best bet for that, since we can get all of the predictions of relativity out of a a subatomic particle. One of our subscribers is trying to defend ethereal mechanics on a website. I forgot to put I'll try to put the link here if I remember. And these people on the website are going off on, oh, you got to write it in Covariant Forum. In other words, it's like name dropping. You got to be somebody that knows somebody. And there are all this, in other words, what it is these people have learned something that hurt their brain in college. And therefore, that's the epitome of everything they know, so that everything must be in that form for any meaning for them, because that is, to them, the highest form of meaning. And therefore, if other things are not in this highest form of meaning, they don't mean anything. Okay? And then that's led me to a very interesting idea. So in the next ethereal mechanics video, we're going to have a new one. I'm going to show and what a covariance is. Covariant form means you put it in a form that's excellent for matrix processing, that shows Lorentz invariance. And I'm going to show you that the cause of Lorentz invariance is nothing more than an illusion. And I'm going to show you with classical physics, and then show you with new electromagnetism that it's just an illusion. And then we'll show you the experiments that are underway, high voltage experiments, which are going to break the illusion. And I'll explain all that in the video. If I try to go into details now, it'll sound kind of hokey, unless I build up step by step so it'll make sense to you. And this high voltage equipment is being developed not only to demonstrate experiments that do not obey Lorentz invariance, but there's other experiments where we need to break the balance, the balance of charge in order to show effects that only occur when charge is imbalanced. Because most of the experiments we've run now are with charge balanced. Most of the experiments that scientists run are with charge balanced. And we're going to show you a simple desktop experiment that when you imbalance the charge, you can see things that you couldn't see normally. So, but we're not going to, we're going to talk about the experiments later. For now, we're going to show you what's going on. The equipment being developed, and you guys let me know if you want me to make videos showing how I'm designing the equipment, you know, with the logic and reason why I select each part. If you want that level of detail, let me know. I'll produce videos on that. But what I've done is I decided to use these cutting boards that you get for $12 at Walmart because I need something to build these high voltage experiments on that are insulative, and also to make the experiments more modular. For example, what I've decided is cut the boards up into subboards that are multiples of 3 inches, 3 by 3 inches. That way I can have a 3 by 3 cube with one thing, a 6 by 6, a 6 by 9, whatever. The reason for that is because the boards are pretty much almost exactly multiples of 3 inches in both dimensions, so it makes efficient use of the material. And the reason why I like this material is it's easy to cut, it's easy to form, it's easy to drill, it's very good resistance, and it's inexpensive. And what's interesting is I'm using a cutting board, and you've heard the expression of breadboard in electrical engineering where they build circuits on breadboards. That's because in the original days of electrical engineering, they actually used boards that bread makers use for bread because they were a good size and you could put a lot of stuff on them. They were all the same size, all the same. So it's ironic that we're going back to using a board for cooking for our electronic experimentation. And this is one of the first modules that are done. This is a high voltage supply where it takes line in. It's got a fuse protection. And the whole purpose is just to give me raw raw DC power. And the reason for this also is that later on, if I decide I need a different board or if I need to replace this because it's not the right kind of power, I need better regulation, then I can just swap out this unit. So that's why the idea for making the boards a uniform size. And also we're gearing up for high voltage. I've purchased high voltage scope probes. These only do 2,000 volts. We need to go, I'm going to be developing high voltage scope probes that can do up to 20,000 volts. Because our first experiments are going to be in the 10 to 12,000 volt range. So this will only probably get me to the point where I can develop the early parts. I'm going to need the other scope probes to go higher. I did find, now what's funny is I did order a high voltage DMM probe, and the picture looked like it was the same size as this, but when I got it, I'm like, holy crap, I didn't realize it was that big. But it makes sense. This is for 40,000 volts. It's a little bit too big than what I need, but I'm going to hold on to it in case I need it. It makes sense because I should have thought, because 40,000 volts at 1 inch per 5,000 volts, that's 8 inches. So 8 inches of protection against arc is what you're going to need. So it makes sense that it's this big. I should have thought of that when I purchased it. I didn't. So and the other thing, the next part that's going to be developed is a 12,000 volt generator. One of the other reasons for the delay is we're having extremely cold weather. Typically the weather around this time of year is between averages about 10 degrees above 0 Fahrenheit. We are now, for the past couple of days, we've been at minus 20, which is causing other work that I shouldn't have to do this time of year. For example, the oil burner's on pretty much all the time, which means I'm burning through a lot of fuel right now. And so I've got my thermal imaging instrument out to find out where I'm leaking heat, find out that I have windows that are failed. They're not broken or cracked, but you can see these are the gable windows here. This is an artifact in my printer here. You can see the magenta, meaning these windows are doing all pretty good. This guy here is all completely dark, absolute black in the middle, which means this window has failed. And if you go outside and take a look at the window, certainly you can see the heat coming through. This is, the dark color means heat is sinking down. On the outside, the bright color means heat's coming this way. And you see the other windows are doing pretty good. It turns out I've got a lot of failed windows, especially on the north side of the house. They got hit by a hailstorm about 5 years ago. Most of those windows are all gone, and that seems to be the bulk of my heat release. But I've also noticed that because my oven is in an island in the middle of the kitchen, they had to route the vent for the oven through pipes under the floor. And you can see this pipe is like 34 degrees Fahrenheit, which is only a few degrees above freezing. So I got these freezing cold pipes just sinking hot air right out the window, outside. There's other parts of the house that are absolutely, the ceiling, shows a ceiling that's absolutely missing insulation. This part I'm aware of because I was up there messing with the insulation and I probably forgot to put it back. There's actually ice forming on the corner of the wall here. My fault. So anyway, thank you for your patience, and I hope this cold weather releases soon so it doesn't cause more delays in producing the videos. Thank you very much.